A JWT library that implements the specification correctly can be vulnerable, not because the implementation contains a bug, because the specification, followed faithfully, includes a mechanism that gives a critical security decision to the wrong party. The algorithm field in a JWT header tells the receiving system how the token was signed. The receiving system reads that field and selects the verification function accordingly. The field is part of the token. The token is provided by the sender. In an authentication request, the sender may be an attacker. A library that treats the algorithm field as authoritative has given whoever presents the token control over how that token is verified. The simplest form of this attack is alg-mon. The JWT specification permits unsigned tokens where no signature is applied, by allowing the algorithm field to be set to the string none. The rationale is contextual. Tokens passed over already authenticated channels or used in systems where signing is redundant may not need a signature. The specification defined none as a valid algorithm value to accommodate those cases. The attack follows directly from that accommodation. An attacker takes a legitimate JWT obtained by authenticating as a low-privilege user, or extracted from browser storage, or captured from an intercepted request, and modifies the payload. They change the subject identifier, elevate a role claim, extend the expiration time. They set the algorithm field to none and remove the signature entirely. A library that has not explicitly rejected the none value reads the field, determines no signature check is required, and returns a successful verification result. The token has been forged. The library confirmed it. This was not a theoretical concern. In 2015, Auth0 disclosed a vulnerability in the jsonwebtoken library. At the time, one of the most widely deployed JWT implementations in the Node.js ecosystems, in which tokens presenting the algorithm as none were accepted by default. The same class of vulnerability appeared in Python JSONs, ruby-jwt, and at least 6 other libraries within the same period. None of those libraries were poorly built. They had implemented a specification that included an algorithm value that should never be trusted in a production authentication context. The alg-mon attack is now well known, and most current libraries reject it explicitly. The algorithm confusion attack is more subtle, harder to identify in code review, and still present in deployed systems where the library's key handling logic has not been updated or audited. JWT supports 2 classes of signing algorithm. Asymmetric algorithms, RS-256 being the most common, use a private key to sign and a public key to verify. The private key is held by the server. The public key is, by design, available to anyone who needs to verify tokens issued by the server. Many systems serve it openly at a well-known endpoint, typically /well-known/jwcase.json. Symmetric algorithms, HS-256 being the most common, use the same secret for both signing and verification. The secret is known only to the parties that need to sign or verify. The attack works by crossing those 2 classes deliberately. The attacker retrieves the server's RSA public key from the well-known endpoint. They construct a new token with modified claims, elevated privileges, and extended expiry, and set the algorithm field to HS-256. They sign this token using the server's public key as the HMAC secret. The server receives the token, reads the algorithm field, sees HS-256, and runs HMAC verification using the key it holds for token operations, its RSA public key. The attacker's signing secret and the server's verification key are the same value. The signature checks out. The forged token is accepted. What makes this work architecturally is that many JWT libraries pass the same key parameter to whichever verification function the algorithm field requests. RS-256 treats the parameter as an asymmetric public key. HS-256 treats the same parameter as a symmetric secret. The library does not check whether the key material is appropriate for the algorithm being requested. The attacker selects an algorithm for which the server's publicly known value is a valid verification input, constructs a token that will satisfy it, and presents a token that passes a check the server was not designed to resist. A third variant, JWK header injection, exploits the same underlying property from a different angle. Some libraries support the JWK header parameter, a field that embeds the public key used to sign the token directly in the header itself. An attacker who presents a token with their own public key in the JWK field and signs the token with the corresponding private key can pass verification against a library that fetches and trusts the embedded key without checking whether the key was issued by a trusted authority. The attacker signs with a key they generated. The library verifies against a key the attacker provided. The check passes. All three attacks have the same root cause: algorithm agility. JWT was designed to encode algorithm selection in the token itself, so that different systems with different capabilities could interoperate without out-of-band negotiation over which algorithm to use. The ability to upgrade from weaker to stronger algorithms, to support diverse implementations, to remain compatible with future cryptographic standards, these were genuine design goals. Algorithm agility serves them. It becomes exploitable when the party selecting the algorithm is the same party presenting a token for verification. The design anticipated negotiation between trusted, cooperative parties. It did not anticipate one of those parties using the negotiation surface to specify the terms of their own authentication. The defense, explicit algorithm allow listing at the library configuration level, independent of anything the token claims, is not architecturally complex. What it requires is recognizing that the algorithm field is an input from the sender, not a property of the system. Systems that do not make that distinction have left the sender in control of a parameter that determines the outcome of the check the sender is subject to. The verification library reads the algorithm field and follows instructions. It was not designed to ask who wrote them.